One of the things that we learned when we were talking about drawing Lewis electron dot diagrams is many times you have to take electrons from one of the outer atoms and make a double or a triple bond in order to make sure that the central atom has 8 electrons. So when that happens, many times there's different choices that you have. For example, with the O3 molecule, you could put the double bond here on this left-hand side, or you could put it over here on this right-hand side. So a lot of times people ask, well, which of those two is right? Is the double bond on the left-hand side, or is the double bond on the right-hand side? More importantly, whenever you can draw more than one correct Lewis electron dot diagram, the term that we call for that is that it's called a resonance structure. So anytime like these are the two different resonance structures for O3, where you've got a double bond on the left-hand side and the double bond on the right-hand side. Now, again, the question comes up as to which one is correct, okay? So although this sentence right here is really important, although we can draw many different resonance structures for a particular molecule, in this case we can draw 2. This has 2 different resonance structures. What actually occurs is actually not either one of them. It's not this one, and it's actually not this one either. As you can see, what actually occurs is a combination of all of those bonds. For example, if a resonance structure shows a single bond and a double bond alternating between 2 different places, like this example right here, what's really happening is that there are actually 2 bonds that are exactly the same length, that are longer than a double bond and shorter than a single bond, okay? It's almost like there's a bond and a half in both places. So this one isn't right, this one isn't right, and unfortunately we don't really have a way of drawing it the correct way, so what do? We draw it this way. Now, how do we know that? Well, because a lot of times we can look at the actual at the molecule, and we can look at it and go, wait a minute. Here's O3 right here. Here's the actual molecule. This number right here is the bond length. Okay, what scientists do know is that double bonds are shorter than single bonds. Because there's 4 electrons, it pulls those atoms closer together. So double bonds are shorter than single bonds. So if that were the case, if we had, again, the double bond and the single bond, one of the bonds would be shorter than the other one. But here's the real evidence of it. We know that in the ozone molecule, that the bond lengths are actually the same, which means it's not this one and it's not this one. It must be, again, like it says above, a combination of both of those. Okay? And then in here, this one here is called the electron distribution one. You can see how the colors, how symmetrical it is in terms of the electrons, which again tells you that those bond lengths are the same. Okay, one way to think about resonance structures, another way to kind of picture it, is think of it as each resonance structure is a different color of paint. So here's one way to draw ozone. Let's call it blue paint. Okay, another way of drawing the ozone molecule is yellow paint. Okay, if blue paint is one, yellow is the other, an equal blend of the two makes green paint, which is the true structure of that O3, that ozone molecule. Okay, so the resonance structure, even though that's the only way we can draw it, the resonance structures do not truly represent what's actually occurring, okay? But based on the rules that we've learned about how to draw Lewis electron dot diagrams, that's the only way we know how to. Okay, and even notice they say resonance structure here, resonance structure here. What does the real molecule look like? They don't tell you. They just say the ozone molecule. Okay, because there is no way using the rules for electron dot diagrams to draw it. So what do? Well, if there's more than one way, and they tell us to draw it more than one way, then we do. So example 1 says, draw the Lewis electron dot diagrams and resonance structures as needed for the following molecules. Okay, so this molecule has 16 electrons, so you're going to have N CS. Okay, like this. That's 16 electron, or no, 14. There's 16 electrons, okay? And then that carbon doesn't have 8, so we're going to take 2 electrons. And one possibility is we can put 2 electrons there, and we can actually take 2 more, and we can put another electron there. So we've got a triple bond and a double bond. Everything has 8, so that is one valid resonance structure. With that negative charge up on the corner, we really should put a negative charge up here just to so when people know, oh, that's why it has that extra electrons, because there's a negative charge. Sometimes you'll even see people put it like this with the square brackets around it, but that negative charge really does need to be there. Okay, so another way of drawing that is instead of a triple bond, we could put 2 double bonds like this, again with that negative charge up there. And then the third way we could draw is we could put the triple bond over here. Okay, and in each case, every single structure does have the 8 electrons that it needs. So NCS minus does have 3 different resonance structures. A lot of times you'll see these double arrows between them as well. Okay, NO2 minus actually looks just like ozone. It has a double bond and a single bond. And again, I'm doing this a little bit quicker. I'm not going through all the steps of the Lewis electron dot diagram, but you can put a double bond on the right-hand side. Again, put that negative charge up in the corner. And then we're going to move that double bond over to the left-hand side. Okay, so NO2 minus does have 2 different resonance structures. Okay, NO plus 5 plus 6 minus 1 equals 10 with that positive charge. So we've got 10 electrons. There are 8 of them. So the nitrogen doesn't have 8, so we're going to move 4 electrons in and make a triple bond. We're going to put, again, we can put those square brackets, put the plus up in the corner. Is there any other way to draw NO where both of them have 8 electrons? No, there is not. So we could say that NO is not best represented by resonance structures. Where NO2 minus, the best representation is with resonance structures. NCS minus, the same thing. Okay, PS3 minus, so 5 plus 18 plus the 1, 24 electrons. So we're going to have 16. So there's our 24. We'll put the little minus up in the corner. Okay, that phosphorus does not have 8. So we're going to take 2 electrons from one side, and we're going to make a double bond. And hopefully you see right away, oh, wait a minute, I could have put that double bond somewhere else. That's exactly right. Okay, I'm going to put the P, and instead of the double bond being down there, I'm going to put the double bond up here. Okay, and then the rest of them are single bonds. Okay, put the negative charge up there. And then absolutely, yes, there's one more where the double bond goes down here. And then the rest of them single bonds, put the negative on it. Okay, and those are the 3 different resonance structures for PS3 minus. Okay, and then SiO2, 4 plus 12 equals 16. This one is very similar to carbon dioxide in that you're going to end up with, this is one way to draw it, and actually very, very similar to this very first one, NCS minus. So that's one way. And now technically, and CO2 is the same weight. And this is probably a little bit more than what you need to know. But if you think about oxygen, again, oxygen ends with 2p4. And if we draw the orbital diagram for oxygen, 1, 2, 3, 4, you'll see that oxygen has 2 unpaired electrons. And so generally, when oxygen forms a bond, oxygen will just will try as much as it can to only form 2 bonds. Because yes, technically you could make a resonance structure where you have a triple bond and a single bond like we did on part A, but because oxygen does typically only form 2 bonds because of that, that actually doesn't happen. The real structure of CO2 is just those 2 double bonds, and actually the same thing with silicon as well. Okay, now again, on a test though, if I say draw the resonance structures, you would draw all of them. But just for kind of for your own knowledge, just know that oxygen, for the most part, does form just the 2 bonds. Okay, now when you might see something like that is, what if I say, I'm not even going to put the bonds in there. What if I say draw this right here? Okay, I'm going to draw part of it for you. So that's how it's laid out. So clearly it's H2CO2. Okay, so in terms of electrons, we've got 2 plus 4, 6 times 2 is 12. We have 18 electrons all total. So let's kind of follow our steps that we've learned. Okay, 2, 4, 6, 8. Remember, no dots on hydrogen ever. So I'm going to fill up the octet for the outer atoms. And the carbon is the central atom, so I need 4 more here. Okay, so I have 18. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've used all of them. Okay, I don't have any more left. Okay, and the reason I bring this one up is because you should notice that this carbon right here does not have 8 electrons around it. Everything else does. So now you have to decide. I need to make a double bond. I need to bring 2 electrons in. Is the better choice to bring these 2 electrons in and make a double bond there, or bring these 2 in and make a double bond there? It comes back to this, that oxygen tries to make 2 bonds and only 2 bonds. So if I bring these 2 electrons in here, oxygen's already got its 1-2 bonds. Okay, it's already made 2 bonds. But the oxygen up at the top has only made 1 bond. So in this case, what would happen is that those 2 electrons from here would come down, make the double bond. Now that carbon has 8. Both of the oxygens are making 2 bonds. That is a better way to represent that molecule. Okay, again, that's probably a little bit more than what you need to know. Again, with resonance structures, this one right here is a great example of, here's 3 different ways you can draw the same molecule. Which of those 3 is actually correct? None of them. Remember, it's a combination of those 3 that is the actual molecule of that compound.